Hey, fellow mathers, before we get into the episode, let's chat and be honest. Think fractions. Y'all, did you understand fractions or did you kind of just survive them?
Like multiply straight across and don't ask questions survive?
Was there a magical click moment?
Or was it more of a slow, oh, years later?
Y'all, tell us your fraction story. We're really curious to hear about how you came to understand more and more about fractions.
Post it, tag us, and use the hashtag #MathIsFigureOutable so we can see it. Now on to the episode.
Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
We know that algorithms are amazing.
Yeah.
Are amazing historic achievements, but they are not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students and grappling with mathematical relationships.
We're so glad you're here to join us to make math more figure-outable. Do-do-do. Okay, so I have a funny story to start with. Funny? Okay. Is it funny? Maybe it's strange. I don't know what you'll think. Okay, so I had this radioactive iodine treatment after I had my thyroid cancer. It's a whole thing. And it killed a bunch of my salivary glands. So you know that I don't produce enough saliva, which is delightful because it's a whole dental thing and all the stuff. But when I talk, I suck on stuff in order to produce more saliva. Uh-huh. And what I have found works the best are these Manuka honey lozenges. But they're huge, so I cut them up into little teeny pieces, and then I just suck on a little teeny piece. If you've ever been in a live presentation with me, you'll notice that I'll go about 10 or 15 minutes, and then I'll just quietly stick something. And so as we are recording podcasts today, I have a bunch of, I cut up a bunch of them. Kim, they come in different batches. This latest batch that I bought, I cut them all up. I put them in this mug that sits right next to my desk, so I can just pull them. They're stuck back together. I can't get them apart. So I'm like digging in here with this pair of scissors, trying to get the little teeny pieces.
Wait, did they stick back together?
They stuck back together. It's like this glob now. It looks like a hockey puck.
Was it maybe humid in your house?
Probably.
I bet the weather's changing.
Well, so. I think it's both. I think it's super humid, and I think that it's this batch because I had a batch before that honestly I didn't like as much because they disintegrated. So then it was all these dust. And I was like, come back together. Anyway, but these are two together. Yeah, it's a whole thing. So I think I finally have enough broken up, but my hand hurts now because it's like trying to break this hockey puck up of sharp. They're sharp. Anyway, you don't care. Okay. There, see, a little personal. Next time you get to share something stupid personal about your.
Okay, all right, I'll think about it.
Or you don't have. I'm not going to force you.
I don't care.
Okay. Hey, I was thinking that it would be fun to do a problem string that I've been doing lately. In fact, I did it with a group of 5th grade kids not too long ago, and I'm just having a ball with this particular problem string.
Yeah.
And I'm gonna make a point about it at the end. Okay. So if you don't mind, Kim, we're going to dive in. We're going to do a problem string, and then we'll make sort of a point about what I love about this particular problem string.
Okay.
So here we go. Okay. Yep. So Kim, picture a candy bar.
Yep.
Okay. It's kind of a long, skinny candy bar. It's not like a fat, squatty candy bar. It's a long, skinny one. It's really long. And what we know, it's kind of weird what we know, but what we know is that 3/10 of that candy bar weighs 12 ounces. That's what we know. Okay, so for whatever reason, we know 3/10 weighs 12 ounces. I'm super curious. Well, should I ask the question first? I'll tell you, with the younger the student that I work with, I will, before I move on, I will say, so tell me about that. And I'll draw a big, long, skinny candy bar.
Yeah.
And then I'll say, help me think about 3/10 of this candy bar weighing 12 ounces. Could we find some tenths? And then I might even ask kids, how would you cut this into tenths? Kim, what do you think kids say when I say, how would I cut this into tenths?
I'd probably cut it in half first.
Often, there'll at least be some kids that'll cut in half. There are definitely a whole group of kids that will just start kind of estimating tenths, and they are relieved when one kid goes, well, can't we cut it in half? And then cut the halves into I'm waiting
5
for you.
pieces.
5 pieces. So then that's not all that easy, right? You try to cut something into 5 pieces equally, but it's easier than cutting something into 10 pieces equally. And so we'll kind of have that discussion a little bit where I cut the whole thing in half, and often I'll make that half line a little bit outside the candy bar so you can kind of see that half line. And then I'll cut 5 pieces on the left, 5 pieces on the right, and I'll label one of those pieces as 1/10. So one of the pieces as 1/10. But we know that 3/10 weighs 12 ounces. So Kim, what could I put on this candy bar to sort of see those 3/10? I mean, I'm kind of asking to read my mind here. I don't know if
I mean, like what you want me to label on the candy bar? I'd put 12 ounces over, or maybe 3/10 on above it and 12 ounces below where the 3/10 would be.
So it's kind of like just 3 of those pieces. And I kind of put a little brace below it to kind of encompass those 3/10. And like that's 12 ounces. So I like it. I like it. We got 3/10 kind of above those 3/10 and then 12 ounces kind of below them. Cool. So we know that. Now, with adults, I don't often do that much. I will just say if 3/10 of a candy bar weighs 12 ounces, then how much does 1/10 weigh? And I'll just ask that. And then if I need to, maybe I'll draw the model. I'm still kind of grappling with if I should have drawn it first or anyway. If 3/10 of the candy bar weighs 12 ounces, how much does 1/10 weigh?
If I know 3/10, I'm trying to get 1/10, then I can divide 3/10 by 3 to get 1/10. And I can divide 12 ounces by 3 to get 4 ounces.
And so what I have written right now on the board is I have 3/10 weighs 12 ounces. And underneath the 3/10, I wrote 1/10. So when you said divide by 3, I literally wrote like the scaling arrow from the 3/10 to the 1/10 divided by 3. And then a scaling arrow divided by 3 from the 12 ounces. And I'm like, oh, what is 12 divided by 3? Sure enough, it's the 4 ounces Kim just said.
Cool. Are you on a ratio table right now? Is that what you just said?
I'm not. I could be. That's interesting. Kim, I haven't never done this on a ratio table.
Well, when you said scaling marks, I wasn't sure if you were. I wrote 3/10 is 12 ounces, and 1/12 is.
Yeah.
But I'm wondering.
I have usually, I've usually written kind of a sentence. Sorry to interrupt.
No, it's okay. I'm just wondering when you said scaling marks. I know what you mean, and I did the same thing, but I.
Well, now you have me wondering if I should put in a ratio table. Okay, I'll try that next time.
Okay.
Next question. So we know what 3/10 weighs. We know what 1/10 weighs. I'd like to know what 1/5 of the candy bar weighs. What do you think?
So I know that a tenth is half of a fifth. So I wrote times 2.
You just said a half and then times 2. That's confusing.
Yeah. So maybe I should say them in the same direction. I know a fifth is twice as much as a tenth. So I wrote times 2 from 1/10 to 1/5. And I wrote times 2 from 4 ounces to 8 ounces. So that's nice. 8 ounces.
How do you know a fifth is twice as much as a tenth?
Because if I cut a candy bar into 10 pieces, I know that my portion is 1/10. But if I'm thinking about cutting something into fifths, then 2 of those tenths is going to fit into the size of 1/5 piece.
So this is often when I will draw a candy bar underneath the first one. So I have a candy bar up there where we cut it into half and we cut each of those pieces into 5. So now I have the 10 tenths. But now in that same size candy bar that's underneath the first one, I'll say, let's cut this guy into fifths. And as we cut it into fifths, I'm looking up and I'm trying to like make those fifth pieces line up with the 2/10 above them. And someone will say, we could have actually done those tenths by cutting the candy bar into fifths and then cutting each of them in half. Sometimes somebody will say that at the beginning, though I'm finding not very often. Yeah. Not very often do people cut it into fifths and then cut those in half. But now we can sort of see that relationship that you were just talking about. We can see those 2/10 in that 1/5. Nice. Okay, so we got 3/10 weighs 12, a tenth weighs 4, a fifth weighs 8 ounces. What about 3 1/5 of the candy bar? How much does that weigh? 3 1/5.
Well, we just talked about 1/5. And I know that 3/5 is 3 times as much as 1/5.
Yeah.
So I'm doing 8 ounces times 3 is 24 ounces.
Brilliant. I wonder if you could also use the 3/10 to get to the 3/5.
Yeah, that's nice. So 3/5 is going to be twice as much as 3/10.
And sure enough, there's that 12 ounces. Oh, sorry.
No, 12 ounces doubled is 24 ounces.
Nice. So 2 different ways to get that 24 ounces. And also a nice way to say that 3/5 is 3 times 1/5, and 3/5 is double 3/10. So sort of really hammering. This is an example, Kim, of when we talk about don't make equivalent fractions into an algorithm. Don't make it be put the denominator down. This goes into that times that. Don't do that. Like help kids really experience tenths and fifths and the relationship between them. And here's a way to do that. Cool.
Yeah.
We're almost done. How about 1/2 of the candy bar? Half of the candy bar. Half of the candy bar.
Mm-hmm. Well, my initial thought, I'm going to give you 2. My initial thought was that I know that 1/2 is equivalent to 5/10.
Oh, nice.
And so I want to go from 1/10 to 1/2 and do times 5.
Because it's like 1/10 to 5/10.
Uh-huh.
Yeah, times
so
5.
4
nice.
times 5 is 20.
So 20 ounces. Okay, great. 4 ounces times 5.
What my other one was going to be.
Shoot.
Man.
Let you think. Take your time. Take your time.
Oh, I can't remember now. It's gonna bug me.
Can I just mention these are ones that kids have told me.
Oh yeah,
which is kind of fun. So one kid said, "Well, we know 3/10, and we're trying to get to 5/10, and we know 1/5. You just said was 2/10. So that 3/10 plus 1/5, the 2/10, we could add the 12 ounces.
So they're
and
thinking
8 ounces.
additively about that. That's nice. Yeah.
Yeah, they're thinking additively. Yeah,
that's perfect.
Another kid, and this might be my favorite. Oh, do you have another one?
Did somebody do 3/5 minus 1/10?
No, but they use 3/5 in a different way. Can you be more multiplicative? Wait. 3/5? Is that what I want? No, hang on. That's not what I want. What do I want?
We're trying to get to 1/2.
Oh, what was I thinking about? That's not. Yeah. Oh, it was what you said. Sorry. It was 3/5 minus 1/10.
So somebody was adding 3/10 and 1/5.
Uh-huh.
And then somebody was subtracting 3/5 minus 1/10. Oh, that's nice.
Yeah.
Good on those people.
Nice, right?
Yeah.
Yeah. Very nice. Nice. And again, really supporting and strengthening the relationships between fifths and tenths is very nice. Yeah. Cool. Okay. Last question. 9/10 of the candy bar. We almost got all of it. Almost all of it. 9 1/10 of the candy bar. How much does that sucker weigh?
I kind of cheated a little bit earlier. When we said 1/10 was 4 ounces, I couldn't help myself to say, like, what is the whole bar?
Thank you for not saying it then. Thank you for, and I work really hard to not have anybody say that.
Yeah.
Yet, until we actually get to this last one. Yeah.
Yeah. So I knew then that the whole bar was 40 ounces because a 10th was 4 ounces. So in this moment, because I'm such an over person, maybe, I don't know, I wanted to do the whole bar was 40 ounces minus a 10th, which is 4 ounces. And I got 36 ounces. Nice.
Yeah. So just a couple other things that kids will often do is that they will say, actually, before I do that.
Oh, man.
So once you have. Yeah. What?
Well, because you could go from 1/10 to 9/10.
Times 9?
Yeah, but I also like.
4 times 9 is not bad. Go ahead.
But I also like the 3/10 to 9/10. I just saw that one.
And that one doesn't come up as, in fact, I think that one's only come up once. And I don't usually think of the 3/10 to 9/10. Yeah. So I love that one. 3/10 times 3 and 12 ounces times 3. It's brilliant because there's so many really nice connections.
Yeah.
And let me just, once you find that whole candy bar is 40 ounces, then you can kind of go back and say, so if the whole candy bar is 40 ounces, does it make sense that a 10th of it is 4 ounces? Sure enough. And that 3 of those would be 12 ounces? Sure enough. And that a 5th, so now I can think a 5th of 40 is 8 ounces? Sure enough. And so 3 of those is 24. Half of 40 is 20. Bam, like all of it. It's just it's a really nice series of problems. Kim, here's the point that I want to make with this string. Well, no, we've made several points, but here's a point I want to make. What algorithm might teachers have been tempted to, or kids are like stuck in using to solve these problems? We really have to work hard to get kids not to use that algorithm for these problems. Like, does it exist? And everyone shake your heads and say no. Like, there is no traditional algorithm to solve these problems. You have to actually reason your way through these. That's brilliant. And I'm going to suggest that as soon as you get out of the 4 operations, that is true. Like, it is true that there are going to be problems that there's just not this method that we want to teach kids. Well, I don't know. There's not this method that we have historically taught kids. I'm trying to find problems like that, to create strings like this, to in part send the message. It's not about one and only one way. It's not about memorizing what somebody has created before you. It's about thinking and reasoning and developing relationships, and think about all the relationships we just strengthened by doing this particular problem string. And we did this string with a group of fifth grade kids. I did 2 of them in a row. First one was rough. Like that we were really getting out what it even means to have a unit fraction of a whole thing and then have 4 of those or whatever. Like we really did a lot of that work, but boy, then we did a rich task with them. And then we did a second problem string like this. And man, that second one, we had some great, like, y'all, it's not that you do it once and if kids are instantly there or not there, oh, we failed, or, like they're done. No, neither of those. It is a trajectory. It's a landscape. It is a continual building and strengthening. That's how we're advocating that we make math more figure outable. We teach math. What do you think?
Love it. Love, love, love.
Sweet. All right, y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figure Outable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figure outable. Y'all, thanks for listening to this episode. All right, listeners, your turn.
What's one fraction misconception that you see all the time?
Or one you used to believe?
Share it, tag us, and use hashtag #MathIsFigureOutable.
Because fractions are relationships, and relationships are figure outable.